Unicast offers significant advantage in terms of network simplicity and compatibility. It requires no special switch configuration. It works reliably across subnets and ensures that each receiver establishes a direct point-to-point connection with the sender, making it the ideal default for most NDI workflows. However, Unicast traffic must be carefully monitored and managed in environments with a high number of receivers per source, such as broadcast production facilities, conference centres or university campuses. Without proper planning, the aggregate bandwidth demand on transmitters and network uplinks can become significant, making the system harder to scale and maintain. In these cases, adopting multicast can reduce network load and simplify bandwidth management, especially when the same source needs to be delivered to many endpoints simultaneously. That's where multicast becomes essential. Multicast allows a single NDI stream to be transmitted once over the network, regardless of how many receivers are tuned to it. When properly configured, the switch infrastructure replicates the traffic only where it's needed, dramatically reducing bandwidth consumption and avoiding saturating the sender's network interface or uplinks. However, enabling multicast in NDI is not just a checkbox. It requires support from the network infrastructure, IGMP, snooping and querying, for example, and an understanding of group management and attention to compatibility across devices and switches. Is also a manual configuration step, since NDI streams are unicast by default. So in this module, we'll examine when multicast is beneficial and necessary, and how to implement it correctly in an NDI environment. We'll also explore IGMP behavior, switch configuration, and common pitfalls to avoid when scaling your NDI system for multiple viewers and distributed locations. As we discussed earlier, NDI uses unicast by default, making it really easy to deploy on even the most basic network hardware. However, proper configuration becomes essential in complex or large-scale installations where multicast is explicitly enabled. Without it, multicast traffic can flood the network, causing congestion, dropped packets, or even complete system failure. This is where IGMP, or Internet Group Management Protocol, comes into play. IGMP acts as a control mechanism for multicast distribution. Without it, multicast behaves a little bit like a broadcast. Every device on the network receives every multicast stream, regardless of whether they requested it. That's like every monitor in a facility displaying the same source, even if nobody's watching. With IGMP, only devices that explicitly request a given stream via an IGMP join will receive it. For example, when an NDI receiver, like a video switcher or monitor, subscribes to a multicast stream, it sends an IGMP join request. The switch then forwards that stream only to the ports that need it, keeping the network clean and efficient. However, this system only works correctly if IGMP snooping is enabled on the switches and an IGMP querier is present in each VLAN where multicast is being used. The IGMP querier is a component that periodically polls the network to maintain group memberships. Without it, switches may not forward multicast traffic, even if snooping is enabled, and this can lead to symptoms such as intermittent stream loss or sources not appearing on receivers. Not all switches handle IGMP the same way. It's important to remember. Some require the querier role to be manually enabled or assigned to a specific device, often the gateway. In contrast, others assign it automatically based on priority. The key takeaway here is that IGMP is essential when using multicast with NDI, but it must be implemented correctly. Both IGMP snooping and a properly configured IGMP querier are required for reliable multicast distribution. And as networks grow in complexity, managing multicast across multiple switches and subnets, well, that becomes a challenge that really does demand careful planning and testing. As NDI systems grow, it's common to distribute sources across multiple subnets, for example, in large production facilities, corporate campuses, or multi-building venues. While unicast NDI streams can be routed manually between subnets, multicast traffic does not cross subnet boundaries by default. This is because routers block multicast unless they're specifically configured to support it. The network must also support multicast routing to make multicast work across subnets, and this requires technologies such as PIM, or Protocol Independent Multicast. And a proper understanding of how IGMP works at the subnet level is also required. These protocols allow multicast streams to be delivered only where needed, avoiding unnecessary network load. However, configuring multicast across multiple routers and VLANs is quite a complex task, and it often involves setting up features like IGMP snooping, IGMP queries, and designating a rendezvous point, or RP, for multicast coordination. In this module, we're introducing these concepts to help you understand what's involved, but in practice, designing and maintaining a robust multicast infrastructure at this scale, well, that should be done really with the support of qualified network professionals who are experienced in multicast routing and IP video workflows. By default, an NDI receiver will only negotiate a multicast stream from a sender in the same local subnet. This is a smart safeguard because it prevents the system from requesting multicast that could never actually reach the receiver. However, if your network is correctly configured and can route multicast traffic across subnets reliably, well, you can allow an NDI receiver to join multicast groups from other networks. This is done through the NDI configuration file, and it's done by explicitly listing the allowed subnets. Here's an example JSON command to let that happen, telling the NDI receiver, yes, it's okay to request multicast from these networks because we know the infrastructure is set up to handle it. You can grab these pieces of code from the read section below me here on the page, by the way. The thing is, it should only be used when underlying multicast routing protocols such as PIM and IGMP query are correctly configured. It's important to note that NDI receivers, well, they can't guess whether multicast traffic will successfully cross subnet boundaries. This behavior must be explicitly configured via the NDI config file. And it only works if the network is fully multicast aware and properly routed. A common misconception is that IGMP and PIM are alternatives, when in reality they serve different purposes and often work together in multicast-enabled NDI networks. IGMP, or Internet Group Management Protocol, is a Layer 3 protocol and it operates within a subnet or a VLAN. It allows receivers like NDI monitors or switches to signal interest in a multicast stream and enable switches to forward that stream only to ports that request it. PIM, or Protocol Independent Multicast, on the other hand, well, this routes multicast traffic between subnets across routers, and it ensures that multicast streams can reach receivers located in different parts of the network. In practice, enabling IGMP snooping and ensuring the presence of an IGMP querier, well, that's usually sufficient in small or single subnet networks. PIM sparse mode, well, that's required to maintain efficient and reliable multicast routing in larger or segmented networks, especially where NDI sources and receivers span multiple VLANs or routed subnets. Understanding how IGMP and PIM interact, well, that helps design a scalable infrastructure where multicast streams reach only the intended recipients locally and across the wider network. Configuring NDI for multicast is a powerful way to scale video over IP workflows in large or demanding environments. While NDI works out of the box using unicast, multicast becomes essential when a single source must be viewed by many receivers simultaneously without overloading the sender or saturating network links. We've seen that enabling multicast in NDI is not automatic. It requires a correctly configured network infrastructure, including switch-level IGMP snooping and an IGMP querier. These components ensure multicast traffic is delivered only where needed, preventing flooding and preserving network performance. For deployments that span multiple subnets, multicast traffic requires the implementation of multicast routing protocols like PIM sparse mode. These advanced configurations will allow multicast streams to traverse routers, reaching receivers across VLANs and network segments, but they must be handled carefully by qualified network professionals. So some key points to take away. NDI is unicast by default, so multicast must be explicitly enabled. Multicast is ideal when many receivers receive from one source. And IGMP snooping and querier, well, they're essential in any multicast-enabled VLAN. PIM sparse mode, well, that's required to route multicast across subnets. Remember, multicast misconfiguration can lead to stream loss, flooding, or instability. And for complex deployments, consulting network professionals is highly recommended.